Okay, we're going to look at implicit relations and ways we can use the derivatives of implicit relations to answer bigger questions. Two key things to remember is that any curve has a horizontal tangent at the points on the curve where the derivative is equal to 0, and a vertical tangent. This one's a little bit rarer. We've done horizontal tangents for a long time. A vertical tangent is any point on the curve where the derivative is undefined. And I'm going to highlight a portion of these statements. Make sure that the points that you get when you do the algebra, when you set the derivative equal to 0, or when you find places where the derivative is undefined, you must confirm that those x or y coordinates that make those two things happen are actually on the curve. It is possible for the derivative to be undefined, yet the function is also undefined. So make sure that when you do the algebra to solve these things, you do end up with points that actually sit on the curve. So let's look at 3 examples of this. Let me move my big head there. I'll move it down here. So we have this implicit relation, right? This relation right here, x squared plus 2xy minus y squared is 18. And I'm asking, where is the tangent vertical? And to find vertical tangents, I'm going to need to find the derivative. And I need to know, where is that derivative going to be undefined? So dy dx does not exist. Where is it? Actually, I like the word undefined better. Undefined. There's my game plan. And at this point, you should be comfortable finding the derivative implicitly. My writing is just hot garbage today. Undefined. And so if you want to practice your implicit differentiation skills, you can do that real quick. Pause the video because I'm going to show the answer in about 3 seconds. 1, 2, 3, and there is your derivative. So I assume you can do that. And I am looking for places where this derivative is undefined. Now, finding those locations depends on what your derivative looks like. And in this case, my derivative, as is often the case in implicit relations or implicit derivatives, my derivative has a fraction. And a derivative is undefined, or a fraction is undefined, when that denominator is equal to 0. So I'm going to find out when x minus y is equal to 0. And all I can say with this is that this will happen when y is equal to x. So I'll say dy dx is undefined when my x and y coordinates are the same, when x is equal to y. Now that's a good observation, but I'm supposed to be finding the points on the curve. I need actual coordinates, like x is 3 and y is 7 or something like that. So I guess it wouldn't be that, it'd have to be 3 and 3 because they're supposed to be equal. But how do we find that spot? Well, if I know that x is equal to y and I'm interested in points on the curve, I need to go back to the actual equation of the curve, which is right here. And I'm going to make a substitution that x and y are the same. So I think I'm going to take my x. If y is equal to x, I'm going to take x and put it in the place of every y here and solve that equation. So this gives me the equation x squared. I'm going to bring it up here. This gives me the equation x squared plus 2 times x, which is another x squared. I'll write 2xx minus x squared is equal to 18. And that's x squared plus 2x squared minus x squared. That gives me 2x squared is equal to 18, which is going to give me x squared is 9. And we get x equals, be careful, plus or minus 3. X is plus or minus 3. And if x is plus or minus 3 and my y is equal to my x, that means the points on this curve where the tangent would be vertical would be the points where my x is 3 and my y is 3. And the other one, when x is negative 3 and y is negative 3. And I'm going to have to pause and restart this, I think. Okay, never mind. I just had a quick thought that was messing up. So that is correct. So ignore that 3-second pause I just had right there. And there's your answer for this first question. The tangent is vertical when the derivative is undefined. And then sometimes you have to do a little bit of extra algebra to find the x and the y. So let's try another one. Let's look at this curve, x cubed plus y squared minus 4y equals 5. And I'm looking for places where the tangent is horizontal. And remember, a horizontal tangent is when your derivative is equal to 0. So we will once again have to find the derivative. And in this case, it is implicit differentiation, which I assume you can do. So I'm about to show you the derivative right now. And there it is. And if I want this derivative to equal 0, I need the numerator to be 0. And so if that derivative is equal to 0, that is going to be when negative 3x squared equals 0, which gives me x equals 0. So that's only the x coordinate. I need the points on the curve. So I'm going to take that x and I'm going to plug it back into the original. And so if x is 0, then we have 0 cubed plus y squared minus 4y is equal to 5. Well, 0 cubed is obviously 0. To solve this, I will need to factor y squared minus 4y minus 5, or at least I hope it factors. And it does. If it didn't factor, we'd have to go with quadratic formula. All right. Spooky. So that'll be y plus 1, y minus 5. And we get y coordinates of negative 1 and 5 go along with the x coordinate of 0. So the points on the curve where the tangent is horizontal would be at the points 0, negative 1, and at the point 0, 5. And there are the 2 points on this curve at which the tangent would be horizontal. And I'm going to piggyback on that same curve and ask you now points on that same curve to where the tangent is vertical. Well, we already have the derivative, so the derivative is here. And if I want the tangent to be vertical, I am now looking for places where your derivative is undefined. I need to figure out what makes dy dx. What is up with my writing today? Dy dx is undefined. Okay, and in this case, again, we have a fraction, so this derivative will be undefined when that denominator is equal to 0. When am I dividing by 0? That's what I'm focusing on. And that's going to happen when y is equal to 2. Well, again, that's not the point on the curve, so I have to go back to my original equation. If you want points on the curve, you always go back to the original. And I'm going to plug in 2 for my y, so that'll give me x cubed plus my y is 2 squared minus 4 times 2 is equal to 5. X cubed, 2 squared is 4, minus 8 is negative 4, is equal to 5. X cubed is equal to 9. And this is going, I need to cube root both sides. So x is going to be the cube root of 9, which is ugly. And remember, for odd roots, you do not do plus or minus. So it's just the cube root of 9. Or you could say 9 to the 1/3 power. And so my point, only 1 this time, where the tangent is vertical is at the x coordinate of cube root of 9 and the y coordinate of 2. And that is it. Kind of ugly, kind of ugly. And I have one more question. I think I said I had 3, but I lied. Let's do one more question. And this one's a multiple choice. I yanked this off of a AP Classroom and I altered it because theirs was way too easy. So we have this curve, x squared over 16 minus y squared over 9 equals 1. And you are immediately thinking that that is a hyperbola, correct? With a transverse axis of 4 and a conjugate axis of 3. Yeah, I just had a phone call from my wife and I've lost my train of thought. So I think we were talking about the hyperbola and I was sarcastically saying that you recognized this as a hyperbola, which is irrelevant. So we have this relationship with x and y. I have given you the first and the second derivatives, and I ask which of the following is true of this curve in quadrant 4. And all of the options are combinations of increasing and decreasing and concave up and concave down. And so we have to remember that those are dependent on the signs of the first and second derivative. And if we are in quadrant 4, your x's are positive and the y's are negative. And so I'm just going to think what happens if I plug a positive x and a negative y into these two derivatives. And so my first derivative, dy dx, in quadrant 4 is going to be 9 times x, which is positive, over 16 times y, which is negative. And that would end up giving me a negative value. And if my first derivative is negative, that means we are decreasing. And so that eliminates a and b. And now the question of concavity, my second derivative in quadrant 4 would be negative 81, which is positive, but I'll write 81, over my y, which is negative cubed, and negative over a negative cube, that will ultimately result in a positive. Therefore, my function is concave up. And so we are decreasing concave up. That is option C. And there we go.